Welcome to The Explainer. Machine learning sounds super complex, right? But what if I told you one of its most powerful ideas is actually pretty simple? Today we're going to demystify it, and it all starts with a really relatable question.
So here's the puzzle. How in the world can a computer predict the price of a house it's never, ever seen? It's not magic, not at all. It's really about teaching the machine to be a detective, to find clues and patterns in the data it already has. That way, when it sees something new, it can make a really smart, educated guess.
Okay, so where do we even begin? Well, with any machine learning problem, the absolute first thing you need is data, right? For our house price puzzle, that means we need some examples to learn from. Think of it like a simple list that connects the dots. For a bunch of different houses, we need to know two things. How big was it, and what did it sell for?
So here's our data. Our whole mission now is to hand this over to a machine and say, okay, figure it out. Find the pattern. We're basically asking it to learn a simple rule, right? Something like, hey, as the house size gets bigger, what tends to happen to the price? Let's dig into how a machine actually does that.
And this is the absolute heart of machine learning. We're not telling the computer how to solve the problem step by step. Instead, we give it the ingredients, our data, and we tell it, your job is to figure out the best possible recipe. A recipe that can take one thing, our input, which is the house size, and spit out the output, the predicted price.
Now, if you're a visual person like me, you'd probably take those data points and throw them on a graph. And you'd almost certainly see a pattern, right? It looks like as the size goes up, the price generally goes up too. So what's the simplest, most basic way to capture a trend like that? You guessed it, a straight line. Okay, but here's the catch. You could draw tons of different lines through those points. A really steep one, a flatter one that's higher up, one that's lower down. There are literally infinite possibilities. So how does the machine pick just one? How does it know which one is the best? This is where the strategy gets really clever. The machine knows that trying to find a perfect line that hits every single dot is a fool's errand. Real-world data is messy, it's never going to happen. So instead, its goal is totally different. It's looking for the line that makes the smallest mistakes overall. The one that's the best possible compromise, the least wrong line, you could say. So what even is a mistake in this context? How do you measure it? Well, for any one of our houses, the error is just that vertical gap, the distance between the actual price and the price our line predicts. The machine's job is to wiggle that line around, changing its slope and position until the total of all those little gaps is as tiny as it can possibly get. Okay, so how does it do that? It uses a really cool mathematical trick. For every single data point, it measures that error, that gap we just talked about. Then, and this is the important part, it squares that number. Why? Two big reasons. First, it gets rid of any negative numbers, because a mistake is a mistake whether you're too high or too low. And second, it makes big mistakes really count. A small error stays small, but a big error gets huge. Then, it just adds up all those squared mistakes to get one final total error score. The machine's entire goal is to find the one and only line that makes that score the absolute lowest it can be.
And there you have it. That's the secret sauce. That's the guiding light for the whole process. By deciding to minimize this sum of squared errors, we've taken a vague idea, find the best line, and turned it into a rock-solid mathematical objective, a problem a computer can actually chew on and solve. This, right here, is the essence of learning from data.
So what's so special about this one best line? Well, it turns out it has a really neat property. All the mistakes where the line was too low, the positive errors, and all the mistakes where the line was too high, the negative errors, they perfectly cancel each other out. Their grand total is exactly zero. It's like the line is the pivot point of a seesaw, and it's found the perfect spot to balance all the data points.
All right, but now let's throw a wrench in the works. Let's get a little tricky. What happens if we add a new rule? For instance, it kind of makes sense that a house with zero size should have a price of zero, right? So what if we force our line to go through the 0, point, the origin? You might think that's a good idea, but it has a really surprising and important consequence.
And this right here illustrates something so important in machine learning. Look at the standard model on the left. That line has freedom. It can slide up and down that vertical axis to find the absolute best place to sit. But in the model on the right, we've handcuffed it. We've pinned it to the origin. By forcing it to go through 0, we've taken away a degree of freedom, and we've actually changed the entire game the machine is playing.
You remember that cool balancing act rule where all the errors added up to 0? Well, guess what? That rule only works because the line was free to move up and down to find that perfect balance. The moment we nail it to the origin, the math that created that rule just evaporates, it's gone. The machine is now working with a different set of constraints, and because of that, it's going to find a totally different line that it considers best.
And this all leads us to a really big final thought. Yeah, machine learning is incredibly powerful. But what this little experiment shows us is that the assumptions we make, the rules we set before we even hit go on the learning process, are just as important as the learning itself. A tiny change to the model setup can completely alter the result, and that's a crucial lesson for anyone working with data.